Hi, I am a tutor in Uplatz. Today we are going to discuss about Linux Part 4, Embedded Linux Kernel and Driver Development Part 1. Kernel overview, Linux features. Linux 2.6.0 was released in December 2003. Lots of features and new drivers have been added at a quick pace since then. It is getting more and more difficult to get support of drivers for recent hardware in 2.4. No community support at all. These training slides should be compliant with at least Linux 2.6.06. We also mentioned features in more recent kernels. Linux kernel key features, portability and hardware support runs on most architectures. Scalability can run on supercomputers as well as on tiny devices. 4 MB of RAM is enough. Compliance to standards and interoperability. Exhaustive networking support. Security, it can't hide its flawed, its code is reviewed by many experts. Stability and reliability. Modularity can include only what a system needs even at runtime. Easy to program. You can learn from existing code. Very useful resources on the net. See the ARC supported hardware architecture. See the ARC directory in the current resources. Minimum 32-bit process with or without MMU. 32-bit architectures, ARC subsidiaries, ARM or AVR 32 is FRV H8300, I386, M32R, M68K, M68K, NO, MMU, MIPS, for RISC can have a 64-bit kernel, but always 30-bit Userspace, PowerPC, PPC, S390, SH, Spark, V850, Extensa, 64-bit architectures, Alpha, IA64, MIPS, PowerPC, SH64, Spark 64, x86 64, C architecture, ARC, kconfig, ARC, readme on ARC documentation, ARC for details. Kernel code, kernel code implemented in C. Like all Unix systems, C was created to improve the first Unix systems. A little assembly is used to CPU and machine initialization, exception, and critical library routines. See http tux.org lkml hash s15-3 for reasons for not using C++. Main reason, the kernel requires efficient code. Programming languages in the kernel sources, SIC 95.78%, ASM 3.9%, PERL 0.08%, YAP 0.03%, SH 0.04%, CPP 0.04%, DX 0.03%, Python 0.01%, DISP almost 0%, and ARC a small percentage. Compared with GNUC, need a GNUC extension to compile the kernel. So you cannot use any ANSI compilers. You can also use the Intel and Marvel compilers only on their respective platforms, which identify themselves as a GNU compiler. Some GNUC extensions used in the kernel are inline C functions, inline assembly, structure member initialization in any order, also ANSI, C99, branch notation, see next page. It requires at least GCC 3.2, see documentation changes in the kernel resources. Help GCC to optimize your code. Use the likely and unlikely statements. Include Linux compiler.h example, if unlikely error, bracket open, bracket close. The GNUC compiler will make your code faster, or most likely case. Use in many places in kernel mode. Don't forget to use these statements. Now, C library, the kernel has to be standalone and can't use Userspace code. Userspace is implemented on the top of the kernel services, not the opposite. Kernel code has to supply its own library implementations, string utilities, cryptography, and compression. So you can't use standard C library function in kernel code. Printf, memset, mymalloc. You can also use kernel C headers. Fortunately, the kernel provides similar C functions for your convenience, like print k memset k memalloc. Managing endianism, Linux supports both little and big endian architecture. Each architecture defines big endian and little endian in ASM byte order.h, can be configured in some platforms supporting both. To make your code portable, the kernel offers conversion macros that do nothing. The most useful ones are CPU, U32 CPU to B32, CPU byte order to big endian, U32 CPU to LD32, U32, CPU byte order to little endian, U32 BE32 to CPU, U32 big endian to CPU byte order, U32 LD32 to CPU, U32 little endian to CPU byte order. Never use floating point numbers in kernel mode. Your code may be run on a processor without a floating point unit, like on ARM. Floating point can be emulated by the kernel, but this is very slow. Define all symbols as static except exported ones to avoid namespace pollution. See documentation code instead for mode guidelines. Kernel subsystems. We have the CPU support code, CPU MMU support code, RAM, storage drivers, storage, character device drivers, speaker, monitor, keyboard, network device drivers, network card, the hardware, file system types, process management, memory management, file support, file system support, device control, networking, and system call. These all make the kernel interface. And we have the C library, user interface, and app 1, app 2, and 3, so on. Kernel memory constraints. What can look after the kernel? No memory of protection. Accessing illegal memory locations result in often fatal kernel oopses. Fixed size stack 8 or 4 KB. Unlike in Userspace, no way to make it grow. Kernel memory can't be swapped out or for same reason. Userspace process, kernel, exceptions, MMU, segment vehicle, attempt to access illegal exception and illegal memory location. Userspace memory management used to implement memory protection, stack growth, memory swapping to disk, demand paging. IO schedulers, missions of IO scheduler, the other reads and writes to disk to minimize disk yet move, time consuming. Slower one is shown and faster one is shown. No, not needed in embedded systems with no orders, data access time independent of location on flash storage. Build your kernel with no op IO scheduler then. Kernel window, overview, Linux versioning scheme and development process. One stable major branch every 2 or 3 years, identified by an even middle number. Example 1.0, 2.0, 2.2, 2.4. One development branch to integrate new functionalities and major changes identified by an odd middle number 2.1, 2.2, 2.3. After some time, a development version became the new base version for the stable branch. Minor releases once in a while 2.23, 2.5, 0.12, etc. until 2.62. Stable versions are 2.4.0, 2.4.2, 2.4.3, 2.4.4 to 2.4.8. In 2.4.3, we had 2.5 branches of to development, 2.5.0, 2.5.2, 2.5.3, 2.5.4. Stable one is 2.6, 2.6, 6.1. Note in reality, many more minor versions in this table and development branches. Changes since Linux 2.6. Since 2.6.0, kernel developers have been able to introduce lots of new features one by one on a steady pace without having to make major changes in existing subsystems. Opening a new Linux 2.7 or 2.9 development branch will be required only when Linux 2.6 is no longer able to accommodate key features but undergoing dramatic changes. Thanks to this, more features are released to users at a faster pace. Since 2.6.14, kernel developer are agreed on the following development model. After the release of 2.6.x version, a 2 weeks merger window is open, during which major additions are merged. The merge window is closed by the release of the test version 2.6.x+1 minus RCL. The bug fixing period opens for 6 to 10 weeks. At regular intervals during the bug fixing period, 2.6.x+1 RCY test versions are released. When considered sufficient disabled, the current 2.6.x+1 is released and the process starts again. 2 weeks merge window 2.6.21 to 2.6.22 RCL, RC1. Then 2.6 6 to 10 weeks, we have 2.6.22 RC2, 2.6.2 RC3, bug fixing period 2.6.22 RC4, 2.6.22 RC5, 2.6.22. Issues security fixes vulnerabilities for two last stable kernel versions like 2.1.6 and 2.1.1, and of course by distribution for the exact versions that are using. Some people need to have recent kernel, but with long-term support for security updates. That is why Adrian Bank proposed to maintain a 2.1.6 stable tree March 2006 for as long as needed years. Still supported during 2008 2.6.16.62. Stable Linux internal API. Of course, the external API must not change. System calls process as it could break existing programs. New features can be added, but kernel developer try to keep backward compatibility with earlier versions at least for 1 or several years. The internal kernel API can now undergo changes between 2.6.x releases. A standalone driver compiled for a given version may no longer compile or work on a more recent one. See documentation stable API nonsense.txt in kernel sources for reasons why. Whenever a developer changes an internal API, he or she also has to update all kernel code which uses it. Nothing broken. Works great for code in the mainline kernel tree. Difficult to keep in line for out of tree or closed sources drivers. USB examples. Linux has updated its USB internal API at least 3 times, fixes security issues, support for high-speed devices, and has now the fastest USB bus speeds compared to other systems. Windows XP also had to rewrite its USB stack 3 times, but because of closed source binary drivers that can't be updated, they had to keep backward compatibility with earlier implementations. This is very costly development, security, stability, and performance. See myths, lies, and truths about the Linux kernel by Greg KH for details about the kernel development process in the link shown here. What is new in each Linux releases? The official list of changes for each of these is just a huge list of individual patches. Very difficult to find out the key changes and to get the global picture out of the individual of changes. Fortunately, a summary of the key changes with enough details is available on the link wiki link. For each new kernel release, you can also get the changes in the kernel internal API. What is next? Document features removal schedule. Documentation lists the features, subsystems, and APIs that are planned for removal announced 1 year in advance. Kernel overview, legal issues. The whole Linux sources are free software release under the GNU General Public License version 2 GPL version 2. See our freeelectron.com article, PSW training for details about the free software release licenses. Constraints of the release time, no constraint before. For any device embedding Linux and free software license and a copy that license, you have to release sources to the end user. You have no obligation to release them to anybody else. According to the GPL, all derived works of the work must be released under the same license, the GPL. Gray area around the Linux drivers are the derived works of the kernel or not. Proprietary drivers are less and less tolerated. Proprietary drivers must not be statically compiled into the kernel. You are not allowed to use reuse code from other kernel drivers, GPL, in a proprietary driver. Advantage of GPL driver from driver developer decision maker point of view. You don't have to write your driver from scratch. You can reuse code from similar free software drivers. You get free community contribution support and code reviews and testing. Proprietary drivers, even with sources, you don't get any. Your drivers can be freely shipped by others, mainly by distributions. Closed sources drivers often support a given kernel version. A system with closed source drivers from two different sources is unmanageable. Users and the community get a positive image of your company, makes it easier to hire talented developers. You don't have to supply binary drivers releases for each kernel version and patch version. Closed source drivers. Drivers have all privileges. You need sources to make sure that a driver is not a security risk. Your drivers can be statically compiled into the kernel. Advantages of having your drivers in the mainline kernel sources. Once your sources are accepted in the mainline tree, they are maintained by the people making changes. Cost-free maintenance, security fixes and improvements, easy access to your sources by users, many more people reviewing your code. Linux kernel wrapper special API, binary block proprietary driver working around the GPL by creating the GPL wrapper. The proprietary blob is not broken when you recompile or update the kernel and driver. Yes, the proprietary driver may not be considered as a derivative work. However, the kernel is monolithic and the blob still belongs to a single executable. This is still controversial. Two example cases, NVIDIA graphic card drivers supporting wireless network cards using Windows driver. In this wrapper project, implements the Windows kernel API and this network driver interface spec API within the Linux kernel, useful for using cards for which no specifications are raised. Drawbacks, still some maintenance issues. Example, NVIDIA proprietary driver incompatible with X.org 7.1, performance issues, wrapper overhead and optimization are available. Security issues, the drivers are executed with full kernel privileges and are all other issues with proprietary drivers. Users lose most benefits of free software. Kernel overview, kernel user interface. Linux makes mounting virtual file system. Linux makes system and kernel information available in Userspace through virtual file system. Virtual files not existing on any real storage. No need to know kernel programming to access this. Mounting proc super sudo mount -t proc 9 /proc. Mounting sys /sys sudo mount -t sysfs 9 /sys file system type. raw device or file system image. In case of virtual file system, the listing is fine. Mount point. See a few examples: proc CPU info, processor information, proc memory info, memory status, proc version, kernel version, and build information, proc CM command line, kernel command line, proc PID environment, calling environment, proc PID command line, process command line, and many more. See by yourself, short by yourself. User space interface document. A lot of details about the proc interface are available in the documentation file system proc task. There's almost 2,000 lines in the kernel source. You can also find other details in the proc manual pages, man proc. See the new device model section for details about sys. Possible to implement user space device service. Possible to implement device service in user space. Such drivers just need access to the devices through the minimum generic kernel drivers. Examples: printers and scanner drivers on the top of the generic parallel port USB drivers, X drivers, low level kernel drivers plus user space X drivers, user space drivers based on UIO framework introduced in 2.6.23. Advantages of user space device drivers: no need for kernel coding skills, easy to reuse code between devices. Drivers can be written in any language, even per. Drivers can be kept proprietary. Drivers can kill and impact cannot crash kernel. Can be swapped out. Code cannot be. Can use floating point computation, less in kernel complexity. Drawbacks: less straightforward to handle interrupts, increased latency versus kernel code. See UIO how to do in the kernel documentation for detailed information and the using UIO on an embedded platform, and talk at ELC 2008. Compiling and booting Linux kernel sources, kernel.org, the Linux kernel archive, download the kernel sources from kernel.org. Linux source structure: ARC architecture specific code, ARC machine board specific code, block layer code, copying, Linux copying condition, GPL, credits, Linux main contributors, cryptographic properties, documentation, kernel documentation, don't miss it, drivers, all device drivers except sound ones, USB PCI, FS file systems, FS extension 3, etc. Include kernel headers, include ASM architecture machine dependent headers, include Linux kernel core headers, init Linux initialization, including main.c. IPC code used for process communication, K-build, a part of kernel build system, kernel, Linux kernel core, very small, lib, miscellaneous library, zlib, CRC32, maintenance of each kernel part, very useful, makefile, top Linux makefile, sets R conversion, memory management code to small 2, network support code, not drivers, readme, overview and building instruction, reporting bugs, bug report instructions, scripts for internal or external use, security model implementation, SE Linux, sound support code and drivers, user code to generate, and intra MFS CPIO archive. Linux kernel size, Linux 2.6.26 sources, raw size 264 MB, 25700 files, approximately 8.5 million lines of code. gzip compressed or tar archive 60 MB, bzip2 compressed tar archive 48 MB better, LZMA compressed tar archive 13 MB best. Minimum compiled Linux size, kernel size with Linux tiny batches, approximately 300 KB compressed, 800 KB raw, Linux 2.6.414. Why are these sources so big? Because they include thousands of device servers, many network protocols, support many architectures and file systems. Linux code, scheduler memory management is pretty small. So the various sizes of Linux is measured in DUS apparent size, size of Linux source directories in KB. Driver is the maximum size, and next is the architecture size. Heading Linux to sources possibilities files the easiest way, but no longer download. Example is given in the Linux 2614.7 tar BAEZ2 or patch against the previous version, assuming you already have the full sources of the previous versions 2.6.1 to 2.6.14, 2.6.14 to 2.6.14.7. Downloading full kernel sources, downloading from the command line with web browser, identify the version you need on the kernel.org. In the right directory, download the source archive and establish a copy of the download address from the browser. wget Linux 2.6.11.12 tar BEZ2, extract the contents of the source archive tar JAX Linux 2.6.11.12 tar BEZ2. Assuming you already have Linux -x.y.n-1 version, and the patches you need on kernel.org with the web browser, download the patches file and the signature. Patch from 2.6.1 to 2.6.1.11 ftp kernel.org pub Linux kernel version 2.6 patch to 2.6 patch from 2.6.1 to 1.1 to 11.12 latest stable fixes can you get by wget. Apply the patches in the right order. cd Linux 2.6.10 BEZcat 2.6.1 BEZ2 patch P1 BEZcat 2.6.12 11.12 BEZ2 patch P1 cd ME Linux 2.6.10 2.6.1.12. A patch file is output file of diff command. So diff minus scenario A make file P make file. A make file 2003.04 diff command minus A make file minus B make file line date info and version and context info 3 lines before change useful to apply patch when line was changed. Removed lines if any, added lines if any, context info 3 lines after this change. Use the patch command. The patch command applies changes to the files in the current directory, making changes to existing files, creating or deleting files and directories. So patch usage example, patch -pn diff line, cat diff line, pipe patch -pn, and bzcat diff line .vf2 patch -pn, zcat diff file gz patch -pn, and n is the number of directory levels to keep skip in the help paths. You can reverse a patch with a minus R option. You can test a patch with the try your own option. Linux patches always to apply to the x.y.z-1 version downloadable in gzip and bzip2 much smaller compressed files always produced for any student. That is what everybody does. Do it too. Linux patch command line example cd Linux -2.6.10 bzcat /patch 2.16.11 bz2 patch pipe patch -p1 cd /mb Linux 2.6.10 Linux 2.6.11 keep patch file compressed. Useful to check their signature later. You can still view or even edit the uncompressed data with VA patch 2.6.11 BZ2 on the fly compression. You can make patch 30% faster by using -SP1 instead of P1 silent. Accessing development sources. Kernel development sources are now managed with the Git. You can browse Linus Git tree. Here, if you just need to check a few files, if you have begun the proxy C Unix environment variable define proxy setting. Example, export HTTP proxy server, COM 8080, export FTP proxy server, .com 8080. Pick up a Git development tree on git.kernel.org. Get a local copy or clone of this tree. Example, the Linux tree, the one used for the Linux stable releases. Update your copy whenever you need it. Linux tree example. More details available in git.rcz. Online kernel documentation, HTTP free electrons kernel doc, provided for all recent kernel releases, easier than downloading kernel source access documentation, indexed by internet search engines, and makes kernel pieces of document easier to find. Unlike most other sites offering this service, to also include an HTML translation of kernel documents in the docbook format. Never forget documentation in the kernel sources. It is very valuable for a way of getting information about the kernel. Thank you.